Hi everyone, thanks for being here. I'm Tristan. These are my colleagues Frédéric and Marie from HEC Paris. This is a theory paper about a signaling game. What's a signaling game? That's a sender-receiver game, pretty much in the way that was presented before, except that I will call it a signal instead of a message to say that this cost to the receiver. And your favorite example, which is the textbook example, is a Spence model where you have a student with a type, which is its ability, and a signal is the level of education that the student chooses. Today, I'm going to use a simplified poker game as an example to exemplify the results. And what we do in this paper is to provide a characterization of the equilibrium payoff of the sender with geometric or so-called belief-based methods. So what we are going to do, and that's what I will show you then with more details, we are going to define the interim payoff correspondence of the sender, namely what are the possible payoff of the sender type by type given the belief of the receiver. And then with this object, we are going to characterize the equilibria by taking a form of convexification of that set subject to the incentive constraint of the sender. So this is what I'm going to explain in details. Where does this approach come from? Well, it has first been used in repeated games with incomplete information. So there is a zero-sum case that I will not talk about too much. I won't talk about repeated games anyhow. But what the spirit of this approach is already present in the hard paper of 85. It has been therefore thereafter applied to the cheaper games. Think of, I have Oman and Art in particular in mind. Of course, the geometric belief-based approach has been popularized by Kamenetsa and Gensko in 2011. And there are recent papers about, there is one with signaling with commitments that you see 2024, another 2024 is about a similar approach as we do, but in the Bayesian persuasion case. But there is no commitments in the paper that we use. All right. So here is a game. Finite set of type. Sender knows its type. Sender can choose a signal which will be in the payoff function, so it will be payoff relevant, and a payoff irrelevant message, a cheap talk message. If you wonder why I need the two, I can comment on that at the end of the talk, and I can, if we have time allows, an example where you can do better with signaling and cheap talk messages. Okay, then receiver observes the signal and the message, chooses an action, game over, they get payoffs. All right. So assumptions in the paper, types are finite. For today, think of signals, actions, and messages, everything finite. But the only thing that we maintain is that the set of types is finite. The rest can be, let's say, compact metric, but just it's irrelevant. Let's think everything finite. All right. One restriction: we need to have at least as many cheap talk messages as there are types. That's the assumption, and I will comment on this later when we see the results. All right. So here is an example. This is a working example for today for exemplifying the result, poker. So simplified Meyerson type of poker. I am the sender, I am being dealt a card, this is high or low. When it is high or low, I can drop out or I can raise some amount of money between, let's say, 1 and an upper bound S bar. Then you get to see the amount I raised, so you can fold and then I get your blind, or you can pay the same amount in order to see my card. High card wins, low card loses. All right, zero-sum game. Okay. Well, that's a signaling game because I send you information and the information is costly because I may lose the amount of money that I raise. So it's a signaling game and not a cheap token. Okay. So very briefly, the notation for the theory part. A strategy is a mapping from types to random signals and messages. A strategy of the receiver is a mapping from signal and messages to random action. Okay, when we have fixed that, I can calculate what's the expected interim payoff of type T. So that's the expression which is there with the integral. It's just the expectation conditional on T. And we are going to need the belief of the receiver. So I'm going to say, just like you did, that the receiver does base rule whenever possible. So whenever he receives something which is in the support, that will be base rule. Otherwise, he's free to choose his belief node as he wants. All right. Okay. So with that, we can define the solution concept, which is PBE, perfect Bayesian equilibrium, which says there is a sequential rationality of the sender, namely, for any of my type, my equilibrium payoff is at least greater or equal to whatever I can get by reporting a given signal or messages. For the receiver, so whatever I observe, signal and message, I must play an action which is the best response given my belief. So it should be in the set which is not a capital Y of my signal and what is my belief. And you see up there the expression for Y, which denotes the set of actions which are bestest responses for the receiver when he has observed signal S and has belief P. Okay? If signal were payoff irrelevant, there would be no S in the Y stuff. Namely, my best response would depend only on my belief, but now it depends also on the signal. Right? Okay. With that, now I can define the main object, which is the correspondence of the interim value for the sender. So script E of SP does a set of payoff vectors, one real valued payoff per type, given the signal that has been sent, and given the belief of the receiver, and for all the possible action that the receiver can take given the signal or belief. So that's why it's a correspondence, because when the receiver is indifferent, there might be several points there, and this is going to play an important role in characterizing all the equilibrium. All right? Okay, so let me skip the rest and just show you what happens for poker. So what happens for poker? Let's say, but then you end up with the bottom red dot, because then if I happen to have the high card, I get 3, and if I have the low card, I get -3. All right, so these are my payoff of the sender in the high type and the low type. All right, now if your belief P is above a threshold, like you're really convinced that I have the high card, you drop out. And if you drop out, I get 1, no matter what is my type, because you have dropped out. Okay, and 2/3, you believe beyond that, is exactly the threshold when you're indifferent. So if you're indifferent, you can randomize between dropping out or raising, and you get this red segment, which corresponds to your belief being exactly 2/3. All right? And as another example, if I can raise, let's say 4, then the payoffs are going to be either 1-1 if you drop out, or +5 -5 if you go in and want to see my card. All right? So this picture is going to play an important role. All right, now perfect Bayesian equilibrium. So it might be that you see me choosing an unexpected signal. So you say, oh, I don't know what you did, I don't know what your belief is, I want to punch. Okay, so it should be possible that you form a belief. You can choose your belief now because we are outside of the support, so you're free to choose your belief. And for that belief, you need to choose some rational action, and that should not be profitable for me. Okay, so necessary equilibrium condition, this my payoff should be above that. So let's not read the details of the formula for the set of interim individually rational payoff, but just look at the thing which is in the box here. V is not interim internally rational if there is a signal such that no matter what is your belief and no matter what is your optimal action, there is always one of my type that prefers to deviate to that signal. And that is a necessary equilibrium condition, I think, obviously. All right, so this is what this set looks like on the example. So basically, that's everything that's in the upper right corner of those colored elements. So everything should be on the upper right corner above the green point. Everything should be in the upper right corner above the blue curve, and that's where you get this gray set. Okay? All right. We are almost done with the characterization, but not yet. There must be a trick. And this trick was invented by Sergio Art in the 85 paper and in the 1.5 paper it was prepared as well. So it says the following. We are going to modify those graphs. We are going to modify those graphs at the point where some states get 0 probability. So we do it like this. So I say that I'm going to consider a pair of VT such that they are equal to the realized pair of U of YST when we're on the support. And they could be anything above when the probability is 0. So why is that? What's the intuition for that? Suppose you have a full support equilibrium. If you have a full support equilibrium, that is all the types and all the signals, then your posterior belief is going to be full support as well. Okay, so that implies that in an equilibrium, there will be the indifference condition for the sender all over the place. But now, how can it be that in your posterior belief, now you assign probability 0 to a type? It is because some time was not sending a signal. All right, so this condition that VT is greater or equal to U something something if P of T equals 0 accounts for the equilibrium condition when you have a non-fully mixed equilibrium. Okay, so that's basically what this thing does. Okay, so this goes like this. Whenever a state has probability 0, I draw a vertical line or a horizontal line, and this is what happens here. Okay, so now this is the augmented payoff correspondence, and I'm almost ready to state the characterization. How much to go?
About 6 minutes.
6 minutes. Okay, this will do. Okay, so here is the geometric operator that we use. Let's call that the flat convexification. You have a set which has 2 components. You have a component in payoffs and in beliefs. And you convexify that set only in the payoff dimension with belief, take it back. You convexify that set only in the belief dimension, keeping payoff fixed. So, example, G is the blue curve, which is here. It is in the VP space. It is not convex. Obviously, G is not a convex set in this 2-dimensional space. And now let me take the flat convexification of that set. That is, I take the convex combination only in the horizontal dimension. So I add the red points and nothing more. Okay. And that reflects the fact that we are going to have the convexification due to Bayesian updating, but the incentive compatibility condition of the sender dictate that this must be made with sender payoff constant. Okay, and this is okay. Let me get there. So this is this notion, this geometric notion gives us the main result. So we have a perfect Bayesian equilibrium payoff if and only if this satisfies those conditions that it is interim individually rational and the payoff belief belongs to the flat convexification of the set I introduced before. So I'm going to show you what it does for poker, but just before that, it's a little bit more difficult to see in 3D than in 2D. So in fact, in 3D, the green curve, which is here, in fact, in 3D, it looks like that. All right, because for all the belief between P equals 0 and P equals 1, you get the same payoff, so it's a segment. So it's like 3 segments. I hope my 3D representation is somewhat clear. And the same for the, let's say, the red curve here doesn't look exactly like that. It's tilted between, because it connects, let's say, -3, 3 to 1, 1. So it looks a little bit like this. And now, if we look at this picture in the P dimension, what does it mean to convexify in the P dimension? How can you do that? Well, you can add points only if, when you project on the V dimension, this curve have an intersection. So in fact, this brown segment here, you can see it here. It lies in the intersections of those curves. So in fact, we see the this flat convexification in the intersection of those curves. So here is an example where there are 3 signals, 0, 2, and 4. So we must be in the gray set because of individual rationality. So the only places where there is intersection is at this point, orange point, which is circled, which is a partially revealing equilibrium, and which is the equilibrium that you would expect. That is, if I have a high card, I raise. If I have a low card, I randomize. That's exactly the equilibrium that you would expect. I mean, that's a simple example of a zero-sum game, and I think many of us teach that. What's funny with this picture, it's easy to prove that if you have a bounded set of possible amount that you can raise, in this equilibrium, you always go all in and you raise the maximum. Okay, that's and I'm going to finish with that. A corollary of the result is that because the equilibrium curves are characterized by this convexification operator, then we know how to bound the number of points that we need in the convexification. Okay, and because of the dimension of the space, then this is why we know that no matter what was the equilibrium we started out with, even if there was infinite set of signals or messages, by using the Caradio-Doric theorem, we know we can always replicate the same payoff with at most cardinality, the number of messages equals the number of states. Okay, so there are examples such as this one. No, I'm going the wrong way. Such as this one. Yes, where we can see that I will stop here. I don't have time, but just that this is a simple example with transparent motifs. That this is a case of sender-receiver games that you have probably heard of, where we can see easily that without chip talk we do worse than with chip talk we do better than without chip. Okay, thank you for your attention.